So let's look at an example of a system of linear equations that we're going to solve using the method of elimination. So I not only want to talk about how the method of elimination works, but why the method of elimination works and how we'll know when elimination is a good choice, an efficient choice to solve a linear system. So in this example, our strategy is going to involve elimination because neither of the equations that we start with has already been solved for one of the variables. Having one of the equations solved for one of the variables in terms of the other makes substitution a smarter choice, a more efficient choice. But that's not the case here. The first equation, 7x minus 2y equals -9, doesn't have one of the variables by itself. Neither does the second equation, 4x minus 5y equals -9. So since neither equation is pre-solved for one of the variables, the method of elimination is a little bit more efficient. Let's choose elimination. And the way elimination works is we're going to take these two equations and either add them to one another or subtract them from one another in such a way as to knock out one of the variables. In other words, that addition or subtraction of the two equations from one another is either going to wipe out all the x's or it's going to wipe out all the y's and let us solve for whichever variable has not been knocked out. So in elimination, the first step in the process is to pick one of the variables to target. That's going to be the variable that our elimination step is going to wipe out, either the x or the y. How do we choose? Well, I like to choose the variable which has coefficients that have a smaller least common multiple. That's going to give us smaller numbers to work with when we do the knocking out process. Once we've identified which variable we want to target, what we need to do is we need to make its coefficients in both equations balance one another out. We need to make them either equal to one another or we need to make them equal and opposite to one another so that when we add or subtract, we're going to wipe that variable out. And this is the step that requires a little bit of creativity. It's the same exact process as balancing a fraction to have a new denominator. Right? Well, what we need to do is figure out what we need to multiply the equations by in order to make the coefficients of that variable we're targeting to be either equal or equal and opposite, and then multiply both equations if we need to by whatever we need to make those coefficients either equal or equal and opposite. If we made the coefficients of that variable equal, then we should subtract the equations from one another. If we made them equal and opposite, we should add the equations to one another. Doing so will eliminate that variable that we're targeting and give us a third equation which has only the other variable in it. And as always, that's what we want to do in a strategy for solving a linear system, because that's going to permit us to solve and get a value for that remaining variable, and then plug that value back into either of the original equations to determine the value for the other. So there's our strategy. Pick a variable to target, ideally the one that's going to have coefficients with a smaller least common multiple. Then multiply one or both of the equations in such a way as to make those coefficients either equal or equal and opposite. Then, by either adding or subtracting the equations to one another, we'll get a third equation which has one fewer variable in it, which we can solve and get a value, and then plug that value back into one of the original equations to get a value for the other. Okay, so in this example, which variable is going to be the smarter variable to target? Which variable is going to have a smaller least common multiple for its coefficients? Well, if we look at the x's, 7 and 4 have a least common multiple of 28. They have no factors in common, so the LCM is just their product. 2 and 5, meanwhile, have a least common multiple of 10. And since that's a little smaller, it's my opinion that it's going to be a little bit easier for us to target the y in this example for elimination. So y is in our crosshairs. And so what are we going to do to get rid of that y? Well, we need to take these two equations and multiply each one of them by something in order to make the coefficient of y in each of those equations equal to 10. Right? 10, the least common multiple. So in other words, I want to make it so that my first equation has a 10y on the left side, and my second equation also has a 10y on the left side. I can do that by multiplying my first equation by 5. After all, its coefficient starts out as 2y, so to make it 10y, we need to multiply by 5. And on the second equation, to turn the 5y that's there into the 10y that we want, let's multiply it by 2. And anytime you multiply an equation, we have to multiply both sides by the same thing. And so multiply both sides of the first equation by 5, multiply both sides of the second equation by 2, and the result of that process will be that both equations have a 10y on the left-hand side. So let's do that step. Multiplying the first equation by 5 and the second equation by 2 is going to give me 35x minus 10y equals negative 45. So that's the first equation multiplied by 5. And then 8x minus 10y equals negative 18. That's the second equation multiplied by 2. And as advertised, we now have a 10y in both of our equations on the left-hand side. In particular, it's a 10y with the same sign both times. So minus 10y in the first equation, minus 10y in the second equation. So our coefficients of y are now equal in the first equation and the second. And that means that in order to eliminate that y, like we're trying to do, what I want to do is subtract the second equation from the first equation. If I subtract the second equation from the first equation, our y terms are going to go away. And here we have to be really careful about signs when we subtract. So 35x minus 8x, when I combine those like terms and subtract, I'm going to get 27x. Negative 10y from the first equation minus negative 10y from the second equation, well, those give us the cancellation we were looking for. It gives us 0y, which goes away to 0. That was the entire point of this enterprise, was to get rid of the y's, and now we have on the left-hand side. Then on the right-hand side, negative 45 minus negative 18 is the same as negative 45 plus 18. That's negative 27. So now we have this third equation, the one written in blue here, which no longer has a y in it, but only has x's. And that's awesome. That's always what we want in a solution, a method for a system of linear equations. Get rid of one of the variables so that we can solve for the other one. And now we can solve for x. All it takes is dividing both sides by 27 and getting x equals negative 1. And everything is downhill from here, right? All the difficult work was to get rid of one of the variables so we could solve for the other, and now we have. In doing so, we found out that the value of x that we need is negative 1. But of course, we're not done. When we have a value for x, we also need that numerical value for y. To find it, I just need to take this value for x and plug it back into one of the original equations. And it doesn't matter which one we plug it back into, because after all, we're finding a point of intersection, which should be on both of those lines. So let's just, for kicks, pick that second equation, 4x minus 5y equals negative 9. Since I now know that x is equal to negative 1, I can plug negative 1, again with a set of parentheses here, into that equation and get an equation that now only involves y. And I'll have to do a little bit of algebra to solve for y. Simplifying on the left-hand side, 4 times negative 1 is negative 4. And now we have a completely simplified expression on the left, so it's time for the reverse order of operations, doing any addition or subtraction that we can to have y have less arithmetic around it, which we can do by adding 4 to both sides. Negative 5y is equal to negative 5. And then dividing by negative 5 to get our value for y equals positive 1. And so we'll package our solution into the ordered pair xy equals negative 1, that's our x, and 1, that's our y. So here we used the method of elimination to solve a system of linear equations with 2 variables and 2 equations. We used elimination. We chose to use elimination, not just because it was written in the problem prompt, but also because neither of our equations had x or y already pre-solved for, right? Both of them came to us in standard form, which is a pretty common occurrence. So we decided to use elimination, and we focused on the variable y to eliminate because its coefficients, 2 and 5, had a smaller least common multiple, which is just going to make our life a little bit easier. And so that least common multiple, 10, is the coefficient that we wanted to make happen for both equations on the y's. We did that by multiplying the first equation by 5 to get a 10y, and multiplying the second equation by 2 to get a 10y. Since our coefficients were then equal, the coefficients on y, subtracting the second equation from the first will get rid of the y's altogether and give me a third equation that only has x's in it. That equation was 27x equals negative 27. That equation can then be solved for x, which we did and got x equals negative 1. And now that we have a numerical value for x, we can plug that value back into an original equation to get a value for y, which we did. After solving for y, we found out that y was equal to 1.